Welcome to this lecture. My name is Mark Scythian. The date today is June 20th, 2024. This video lecture is titled Solar Power, the AC Power Inverter, and Electromagnetic Induction, or EMI, Grid Amplification. So these are three principles and applications that support practical household solar power. So assume that we have a 10 solar panel configuration that's set up for a household that's converting its at least supplemental power into solar or even primary solar power. Now, it needs to be known that the practicality of solar panels is based on grid amplification, or the culmination of many households' solar panels then transmitting their power to a centralized charge capacitance, which can then be returned at various outputs that are within the statistical probability of kilowatt hour usage per home. So in fact, there's an overproduction of power, but a single configuration per household would mathematically calculate to impracticality. So let me explain in the three parts. So assume we have 10 solar panels connected together in series, and that means we're wiring the direct current that discharges out of the solar panel with respect to positive to negative and then negative to positive. So series circuits, they maintain a constant current while accumulating or having the ability to adjust or vary the voltage. So with direct current circuitry, we are dealing with electricity flowing only from positive to negative. So this is not the alternating current and voltage, sinusoidal or sine wave alternating or oscillating back and forth. Instead, this is just like battery power. So think of each solar panel as a battery electric source for which the sun delivers 1,000 watts of solar thermal power per square meter. So 1 square meter of area with sunlight exposure will deliver or absorb 1,000 watts of equivalent power to the photothermal effect. So what this means is that we have plasma particles in the sunlight. So light itself are photons, and they are both particles and waves. So we have light at a wave function, but it's also carrying materials and particles or matter through that light. So if we come up with a simple standard, how much equivalent power is 1 square meter of sunlight, the answer is 1,000 watts. But however, we need to get that into electricity, or at least electrostatic potential, sort of like charging a battery. So the material which comprises solar panels is such that its energy density is set up to absorb the photons of sunlight at the 1,000 watt per square meter indicated power input, and then absorb only 20% of that into an electrostatic charge. So if we actually discharge the electrostatics into electrodynamics, or actually flowing electricity, each solar panel, let's say a GEP VP 200M solar panel, they're approximately rated at a 200 watt output. So there's about a 20% conversion rate from solar thermal power to actual direct current electrical power. So DC electrical power output at the median range of sunlight exposure, minimum, maximum. The commercially sold solar panels are designed to then discharge 200 watts per panel. So we're taking these 200 watt solar panels and we're connecting each panel so the wiring goes from positive to negative, positive to negative, and then negative to positive. So if we started on the first panel, positive goes to negative, and then negative goes through the panel itself and comes back to positive, then positive is then going to negative, and so on and so forth. So we end up completing the entire circuit as a continuity circuit, meaning none of these solar panels can fail, or else the entire configuration fails as well. However, the function of series circuits in electricity is to maintain a constant current. So no matter how many solar panels we connect in series, the total current remains constant. However, only the voltage will increase based on the sum of each voltage rating. So there's approximately 20.3 volts DC per panel. And so if we multiply 20.3 times 10, we get 203 volts DC, as in 203 volt battery. That's the equivalence. And then we have a total wattage of 2000 watts DC. This allows us to then divide the wattage into the voltage to calculate that constant current. So in this case, it's 9.85 amps. So out of the completion endpoint of the circuit, the positive and negative, when hooked up to the AC power inverter, will receive 2000 watts of, I'll call it battery power because it's direct current, and then divided into the 203 volts of, again, 203 volts of battery power. So each solar panel is acting like a battery, and it's charged by the sun. So you have to look at it like you're putting battery packs on your house and the sun is charging those battery packs. And so the totality is, we can draw the 9.85 amps, 2000 watts, 203 volts, and then send these charge clusters into a AC power inverter, which simply converts the DC battery power or direct current into alternating current. So that's an AC, it's an electronic AC power inverter rated and designed for the household alternating current true power applications of usually 110 VAC at 60 cycles per second or 60 hertz. So you may have 120 VAC at 60 or 110. So the AC power inverter converts DC or rectified bridge electrical power to AC sinusoidal wave current and voltage. So what that means is just converting from DC to AC. So battery power converted into household electrical AC power. And that again is at 60 cycles per second in the household AC power metric. And so at the standard household AC electrical power metrics of 110 VAC, 110 volts AC at 60 cycles per second or hertz frequency. So presently in 2024, commercially sold AC power inverters function at an impressive 95% efficiency. So a lot of research and development's come a long way, even in the last 5 years, and the prices come down substantially. So overall, the most expensive component comparatively to the solar panels is the AC power inverter, and the installation costs more or less. So a lot of these are subsidized, but anyway, if we get down to the practicality, we could take 2,000 watts DC, multiply it times 0.95, so we get 1,900 watts of AC true power, which is not a whole lot of AC true power. Okay, so if we didn't have a power factor involved, we would then only have the AC apparent power down here, and that would be measured in volt amps or potentiality. And so when they're talking about effective versus peak values for voltage and current, they're talking about the sine wave. So assume the sine wave that regulates the current. We should have two sine waves in AC, one for the current and another for the voltage. And the current's in red, the voltage is in blue. And so you notice that they reach their crest, trough, and they're alternating back and forth at a certain frequency. So in this case, you're going back and forth from the power station to the household. That power station could be the inverter itself, but wherever the AC is harnessed. And so they're going back and forth from the quote unquote power station to the device back and forth 60 times per second. So if we just isolate one portion of these cycles as over the function of time, which is the line, the black horizontal line, the x-axis, and so we have the sine waves for the voltage. The sine wave for voltage is leading the current by a certain phase angle, right? And so that phase angle is the phase shift angle, and that's an actual value. So we're just making an example here, but if you took the inverse trig function of inverse cosine of the phase angle, this would calculate the power factor. Or you could take the AC true power in watts, like AC watts, and then divide it into the product of the effective current or effective voltage times effective current, and that should be a value at the highest of 1.0 to less than 1.0, so it's more like a coefficient. Okay, so what's important is that we have peak positive and peak negative values with the AC electrical power, and that is the function of the voltage and the current sine waves. But however, what you get to use at the outlet is exactly 0.707 of the peak value. So if you took 1 over 0.707 times your 110, you would get something like 153 peak, positive 153 peak volts, and then negative 153 peak volts, and then on, negative, positive. And so you get to extract the root mean square effective voltage and current, which is exactly 0.707 of the peak. So you're getting that 110 volts as 0.707 of the peak volts. And it also works like that with the current as well, the peak current, the peak voltage. So we got I representing current, E representing voltage, and so I sub P and E sub P are the peak current and voltage values, but the 0.707 is what you actually get for effective or practical usable voltage and current. And so the advantage is that if you have a change in your load, the phase shift can change and add or subtract current or voltage or wherever it's relevant to then regulate the power output. So nothing really changes. It's like it's its own governor. If this is a mechanical or an electronic governor, this is like a electroharmonic governor. We'll put it like that with the AC. So that AC alone can do all its self-regulation. So, like for example, if this was AC power going to an electric motor, the voltage would govern the RPM of the motor, and the current would govern the torque of the motor. So if we multiply the RPM times the torque times 2 pi radians, or 360 degree circle, one rotation, and then divide it into 33,000 foot-pounds per minute, if we use that equation, we would then have the brake horsepower of the electric motor. But we also have to factor the efficiency loss. So it's about 85% efficient, and we can then factor in the brake horsepower formula and take out from that the efficiency loss. But what's the most important aspect is the load on that motor could change. So of course, an instantaneous drop in torque would occur under the load. So again, the current can be advanced a little bit forward naturally. It would always maintain its power value. So it doesn't like it when a little bit of load comes on that motor. So the sine wave for current would automatically advance itself to compensate for that drop in torque, equal and opposite increasing torque. So there's a constant delivery of power, whether under a load or not a load, whether under a load or no load. So that's a really important aspect of having a non-physical governor or an electroharmonic or electromagnetic type of a governor. So that's what makes ACs so practical out in the real world. You can make higher voltage, lower current. You can make the gauges small. They don't have to be strand. They can go for miles. So you're basically having a type of electricity that's behaving in the likes of a radio frequency wave, but at much lower frequency. So then it tends to become more an electron particle than an electron wave, even though it's still bound under both. The totality is functioning as a oscillatory sine wave, but it also has the ability to alternate back and forth. And this is through the RLC circuit. So again, this is not a lecture on AC electrical power. There's other lectures in my YouTube library that can be accessed, but it's about the practicality of solar panels. So again, this AC power inverter converts the DC equivalent battery power coming out of the solar panels into AC household electrical power. Okay, so that's, and again, it does not have the moving parts. This is not a mechanical inverter, purely electronic. Long ago, they had mechanical inverters, a battery driving a DC motor, then driving an AC generator, and success. You've converted DC battery power into AC electrical power, but use the DC motor driving the AC generator, a mechanical system, right? And in the last 20 years or so, 25 years or so, the AC electronic inverter hit the civilian market because, this goes back some time into the military industrial complex R&D, and it was at one time very practical to market down in the commercial civilian market because the materials were still set up for analog electronics. And when digital electronics, their materials came onto the market, all the so-called advanced and complex applications became super simple and cheap to mass produce. So anyway, those who are probably much younger have only known electronic inverters, so that might be very antiquated. But if you're in the aircraft industry, you go back to some older helicopters, you can see the mechanical inverters. You can see them on boats and other industrial grade vehicles, but it's important to know we don't have any moving parts. It's a purely solid state AC power inverter designed to take battery power or equivalent DC power from solar or any other DC electrical power source and convert it the opposite direction into AC instead of AC going through a rectifier diode bridge and made into DC. It instead does the opposite. It goes from a rectified bridge DC direct current into AC current. So once that inverter is connected, we then have all of this going on. It behaves just like any other alternating current application, but at the 60 cycles per second. Like aircraft, it's 400 cycles per second, aluminum wires, a lot of that. So none of that, just household AC power, 110 at 60 hertz. Okay, so now we've succeeded in converting the 1900 watts of AC true power, or the 2000 watts of DC power, into 1900 watts of AC power. Okay, so now the practicality is that we have to take the power factors are varied. Okay, they could average between 0.75 and 1.0. So if you're dealing with an AC heating element or even many light bulbs, they're close to or at a power factor of 1. So more or less the multiplication of the effective voltage and current makes a power factor 1.0 circuit behave much like a DC circuit. So you can just multiply the effective volts times the effective amperes and get a very close or exact value when dealing with 1.0 power factor application. So again, we're multiplying go back up here, we're multiplying the effective voltage times the effective current times the power factor to get the actual true power output in watts. But if we only multiply the effective volts, AC RMS voltage times AC RMS current, we will only get volt amps because we're excluded the power factor. So usually like light bulbs and heating elements, they'll be about 1.0 if they're AC. But electric motors and anything having to do with motion, electromotive applications, converting electricity into motion or velocity like motors, etc., then we have approximately like 0.65 to 0.8, 0.78, something like that. So the average is around power factor of 0.875. That's average of, because you need that power factor to actually get the watts, right? So if we take that assessment and then we multiply the average of the power factors, we can get a fairly accurate return value on the grid amplification. So here AC heating elements and most light bulbs tend to maintain a constant power factor close to 1.0 PF, whereas AC electric motors or AC electromotive applications have on average a power factor of 0.75. And so the effective or RMS AC current at 1.0 power factor would be the 1900 watts of AC true power discharging out of the AC power inverter, then divided into 110 times 1. So it's about a theoretical 17.3 amps. But when we start to average the minimum and maximum power factor, then we have a more real world practical value, because if our power factor drops, we then are incurring greater amperes. So it's about an average value of 20.15 amps. So we'll just say 20 amps is what you can get out of 20 amps AC at 110 volts, 60 cycles per second, is what you can get out of 10 panels. So that might seem pretty insignificant, but nonetheless, it might be perceived as being able to power maybe a refrigerator and a well pump or something, and that's about it, like backup power. But where solar actually gains its practicality is when, let's say we have 10,000 houses, each having 10 solar panels, and they're sending about 20 amps of current all together. So we have approximately 201,500 amps of AC current being sent through, let's say, 2,000 volt AC volt high tension lines, utility lines, and then they go to a power distribution grid throughout daylight hours and nighttime hours, just a grid. And so incurred is the charge capacitance, and then a strong electromagnetic field and its induction. So that EMI grid acts like a giant inductor, where we can then establish this giant LC circuit or inductor capacitor circuit. We then reach charge capacitance and then derive surplus electrostatic potential or surplus equivalent electrical charge. But interestingly, this LC circuit's like a giant AC. If there's such thing as an AC battery, that's what it kind of is. So it's just going to be known as charge capacitance and EMI induction. But because it's so large and all these houses are so-called communicating electrical current, it then incurs a surplus electrostatic potential, or electrical charge potential will occur within utility power network. So in other words, sufficient AC power return to households during daytime and nighttime AC electrical power demands. So if we took 10,000 households times 20 amps per household, we get 201,500 amps of AC. Multiply that times 110, and then we multiply that again times the value of the average power factor. So if we take 1 plus 0.75 divided by 2, we get 0.875. So almost 0.88, which is about right. So if we wanted an average power factor for anything that runs on AC, it's about 0.88. And so the actual measured value will be right around 19.3 megawatts of AC true power out of 10,000 households with solar panels. And so if we then break that back down into each household, this will overproduce power by at least 25 to 50%. So we'll just say 75% or less of available solar derived inverted return power. We'll just call it inverter return power from each household. So 19.4 megawatts, which is kind of like what a large Siemens gas turbine, land-based gas turbine electric generator system would produce, about 20 megawatts for a community of about 10,000, 15,000. So this actually now becomes so practical and cost effective. Instead of each house having its own little solar power, having its own solar power would only be good for supplemental power. You might just get about 20 amps out of those solar panels in AC. But when you combine all the solar panels into a central EMI grid, there then becomes a charge amplification. It's sort of like, drawing a few PSI out of the tire, but then you have 40 PSI of charge in that tire. So the electrical version of an accumulator is a capacitor. Okay, so in this case, it's kind of having way more power than you need, but then having the availability when it's needed. And there's never been a time when all 10,000 people in any community, or 100,000 or 1,000,000 people, all turn every circuit on in their house. Like turn on all the lights, turn on the dishwasher, turn on the dryer, turn on the washer. That's not going to happen, right? So that's what the household rating is at, as if everything's turned on. And so you have about 50, as little as 25% of a demand or a current draw per house. So overall, it's about less than 50% from total peak power draw in each household. And so you need at least 50% of that, and you get about 75% return. So there's an overproduction of power. So why is this relevant? Is because, the sun goes down, people are wondering, okay, how are you going to get your power now? Well, you have several days, if not weeks, of power in storage from all these solar panels, sending their electrical power first through an inverter, and then some pretty high overproduction of current, 201,500 amps of AC effective current, all accumulated and charged at a central EMI grid through the power utility companies. So what this guarantees is that whether if you're at nighttime, maybe you throw a party at 3 in the morning, you're going to have the electrical power, because how many other people are doing that? It's not going to be, it's going to be 1 in 5,000 will do something like that, right? So you can play with the stats all you want, but if you go into the probability stats, the actual real statistics using probability curves, this is reliable, as in its reliability factors approaching 1 at 1.5, even 2. So then the next step was to then make the cost of solar panels less expensive, mass production, 3D printing, a lot of AI research along with welcoming outside the box research with material science. So many skeptics of solar, everybody in engineering kind of it has been, but not so much on the material science. Like, ask us if it's practical a couple years from now, not now. We're here now. We're here at that time when the material science has actually, made decades, if not half a centuries of breakthroughs in the last 5-6 years, comparatively. So now you can crank out a 3D printed solar panel, pennies on the dollar, and it's got a guaranteed 200 watts. And same thing with these AC power inverters. This is really why it's so valuable, effective, is that you have such a high conversion rate now. And so, make a long story short, you're just taking solar panels, treating them like they're little batteries charged by the sun, converting that DC battery power to AC, sending the AC out away from the house to the central grid, let's say times 10,000 houses, and then incurring a charge capacitance and an EMI amplification, electromagnetic induction. So it's like putting a giant capacitor and an inductor together elsewhere, and then the return AC power is 25% more than peak demand. So what does this all mean in just a few words is that whether you're at night time or daytime, for regularly average use habits, etc., you'll have electrical power. And even if we didn't have solar, how many people would turn on everything in their house? Like, out of 10,000 houses, nobody's ever had event where all 10,000 houses turned everything on. Dishwasher, lights, garage door opener. Open and close the garage door. Nobody's done that. It's an experiment, sure, but that's not what people would ever think about doing, right? So then you may run into some power with demands, but assuming you didn't have AC solar panels, you would see some sort of I wouldn't say a brownout or a blackout, but you would have a over demand situation. You get a notification that there's an excess amount of power consumption. You get a request to decrease your power consumption. That does happen when some commercial operation is occurring and a huge amount of power draw takes place, or from the thermal thermistors or thermal based resistors going into fail-safe mode during heat cycles. And that's also another source of delayed or compromised power, right? But you may get something to where a grid would shut itself down, not because of failure, but of protecting itself from overheating and or insufficient power availability. But you'd have to be doing something really extreme for that to happen. And sometimes there are big operations that draw a lot of power on the commercial end, and that causes some residential deficiencies in electrical power. But that's not normal. That's like some has to happen, and so they'll just compromise electricity for a few hours. But what is relevant is that you're not going to have all 10,000 or 100,000, whatever, houses all turn everything on in their house, all lights, everything that runs. You don't see that happen, right? So unless that happened, your solar panels are equally reliable, provided it's not each house to itself, but every house sending out, communicating, or quote unquote broadcasting its amperes of AC out from the inverter from each house to a centralized grid, and then overproduction of power and charge potential occurs, and then it can be returned back whenever residents need that power. And so this, in the long run, then eventually gets the price down of electricity. And there's a lot of subsidization going on. And so, I think we're here now to where solar has a practicality, and it's not just insufficient amount of current at a high expensive price, and people saying, oh, it would take you 29 years to pay your solar panels off, but yeah, okay, congratulations. But now it's not like that, mass production. So now it's not even an issue. You can actually get more people solar saturated to the point where it's almost like people don't believe their electric bill's so low, and they're used to just the old way. But we're getting a lot of nothing's free, but kind of, I guess the sun is free. There's actually no strings attached to that one, and we can draw just like we have our magnetosphere. We could actually draw electrical current off of the Earth's magnetic field. We definitely can get it off the photons from the sun, at least in this research and development. Now we're in the mainstream with this. The Earth is also storing enormous amounts of electrostatic potential from all the photons that are delivered onto the sun, and then they charge in the Earth's elements and minerals, etc. So the Earth itself, the crust is 853 miles thick, and we have an 8,000 mile diameter Earth. So there's just massive amount of resources and a sea of electrical current or electrostatic charge in the Earth's crust. But at least we could start with the electrostatic effect in the air as the sun's neutrinos and magnetic particles then reach some type of a gross matter like the Earth's atmosphere. Then they convert into photons and what we perceive as light. So we have to look at the sun as somewhat similar to the endpoint of a black hole, which is the white holes, what you see. But out there, you have the massive amount of gravity, which then crushes or implodes the helium and hydrogen atoms and or their ionization of atoms. But the idea is that they're releasing atomic energy, and then that's converting into the neutrinos and magnetic particles. And so nobody really knows what the sun is. I mean, it'd be lying if they did, but it is some sort of a transformer at a very minimum that is taking even informational, quantum information, and recognizing that under extreme gravitation, very similar to a black hole, and then converting the fission of helium hydrogen into the discharge of neutrinos. So it's more like a nuclear physics or a nuclear reactor sort of, and then out of that you get the charged particles of neutrinos and a corollary magnetic photon, which doesn't exist, but magnetic particle, or we could say it's a wave particle, magnetic wave particle, but only when it hits a gross matter like the Earth's atmosphere, then it becomes wave particle duality of light, and then we have the photon, light itself. So we're actually carrying tangible plasma material in that sunlight, which then can be measured practically as 1,000 watts per square meter of photothermal power, but we want photoelectric or photovoltaic power. So we build a solar panel to convert the solar thermal power into solar electric power. And all we get out of that is battery power, DC power, 200 watts. But then we send it through an inverter, and then we get now 95% of that converted into AC electrical power, which is very impressive. Material science have changed, 3D printing, AI, assistance, all that's made this practical, made us actually not a pipe dream, but something commercially sold now in a short span of 5 to 7 years. Pretty impressive. And so we're here now at the point to where this industry can be blown up, and the long-term effects, we know that whole environmental aspect is a double-edged sword. Yes, there's as many pros and cons. There isn't just all pros, all cons to any issue out there, especially environmental issues. So we'll say that there's a balanced number of pros and cons environmentally, but infrastructurally, there is a whole lot of benefits now that this charged capacitance EMI grid amplification can then make solar very practical, as if everybody's got a set of batteries on their house and then they're getting a overproduction of AC power. And we don't mean you're creating something for nothing. It's still obeying the conservation of energy. It's still obeying the first law of thermodynamics. We are not creating more energy output with less energy input, not at all. But what we're doing is we're just taking advantage of charged capacitance and having a larger inflated tank so we can send it to the smaller ones, each little house, under the proper demands. But to actually do that on a conventional method, it's absolutely the practicality of how conventional hydrocarbon combustion fuel power generation works. It's still pretty much the standard with natural gas and steam power, and then we have gas turbine engine fuel like kerosene, converting gas turbines into power large AC generators, right? So that's still, mostly the system, but with the charge capacitance, it's a better power distribution method. So now with the practical demands, you have a practical overproduction of power, not an actual overproduction of power. We're talking about conserving you're not going to get more out than what you put in. But we're talking about organizing the electricity based on having micro batteries on every house. We call them solar panels, right? So that's kind of, it's simple, but it's a little tricky to explain because it seems like, oh, that person has solar panels, so they're self-sufficient. Well, it's kind of interdependent system. So the more solar panels you throw on houses, the more you connect them all together, the more people end up with lower electric bills. And in the long run, there's just more reliability because you don't have to have the sun on those solar panels all 24 hours a day. You could get a pretty good return charge off just 8 or 10. And if you live in a very sunny state, I live in Arizona, so super practical over here. But that doesn't mean Washington State or other less sunlight or hazy states, we'll call it, can't take advantage of the minimum solar inputs because it's still an approximate value and it's still very close to the return power, especially with the population tends to be a little bit lower in colder environments, not necessarily like we have Chicago and et cetera. That might be an issue in Chicago, but if we look at many places that are not big cities, then we have less of a demand anyway, and then our charge return is about constant as what it would be in a larger metropolis where sunlight is very prevalent, like a desert, right? Like California, Arizona, New Mexico, etc. So this is the basic premise to where at one time it was a bit impractical. And engineers, scientists, not all of them, many are in R&D, and they were just quiet until this day comes upon. But, most would be like, when you get a charge capacitance system, or you can actually get the efficiency high enough in the inverter, then okay, it's something we could talk about. But we're here now. Things have changed so much, and they're going to continue to change. Only thing constant is change. So the change is good when the improvement is followed, and seeing where it's going becomes very interesting. And hopefully this keeps people engaged with the concept of, or the actuality of, changing reality. Because if you find out where it's really going, then it can be very interesting. We'll keep it like that. So this isn't 4 years ago or 6 years ago. This is now, and even now is gone. We're gone a few weeks in the future now. Technologically, just one day of R&D is moving so fast. So I'm just saying, there's still a lot of people that are like, we don't want to do solar, And now it's getting very practical. Even many of us engineers would be like, okay, now we see where it's gone. And getting the knowledge and the education about present solar breakthroughs, I think, is more relevant. So that's the three stages of practical household solar power and harnessing it thereof. So we'll just go over this just in about 10 seconds here. Solar power, number 1. AC Power Inverter, number 2. So that's converting the DC electrical power from the solar panels into AC household power. But then we're not sending it to the house. We're sending it to a centralized grid, incurring EMI grid amplification, and then it's returned back to households based on demands. And so this is so practical at nighttime hours, but it requires more houses getting solar panels, and then everything just pays itself off, and then the price of electricity comes down. And that's kind of just a very solid state, no moving part, self-correcting, regulating system. It's kind of something that people don't have to really be bothered with constant upkeep. And so yeah, there's going to have to be a shift in the economics a bit. People in other potential energy sources, coal and gas, and now we have the sun as a potential kinetic energy source, and then into all the solar output. So there's a little bit of a learning curve if people are not in the STEM world. They're not physics or engineering majors, chemistry majors, but people are in the skilled trades. There's a few courses they can take to then continue on their job and now work with the photovoltaic cell and inverters, or the solar panel inverter. So that's about it for me. And this lecture, I tried my best to keep the viewer engaged onto the practicality of the solar household power systems. But there's also a little bit of a learning curve, because if we oversimplify too much, we miss some very critical details. And it's really in the EMI amplification and return power. This is where it becomes so practical, the solar panel applications. So thanks for staying with me for this long on this video. And again, I try to keep these lectures brief, but there are some intricate details that if they're explained better, then it's not very difficult to understand the bigger picture if those details are touched upon. And anyway, thank you for watching this video, and have a great day.